Thank you everyone for tuning into my presentation today. The title of my talk is Challenges of Boundary Conditions in Open Ocean Models. The development and calibration of coastal numerical models to support engineering design and environmental impact studies is a challenging process, and one that requires professional judgment and continual assessment of all aspects of the model makeup. Open ocean boundary conditions are typically the most complex and important aspect of a model build. They represent the influence of dynamics occurring beyond the model extent, bridging large-scale dynamics to the small-scale processes in the model. In this presentation, we will look at the challenge we faced regarding open ocean boundary conditions on a recent project and how we utilised data to achieve an effective model. Before we get into the main slides, here is an outline of the presentation today. First, I will introduce the case study, which is the Merimbula STP Upgrade and Ocean Outfall Concept Design Project. We will then look at the model development and calibration approach, the challenge we faced with Regional Ocean Modelling System ROM's boundary conditions, the design boundary condition approach we adopted and model results, model limitations, and we will finish with some key considerations for future projects. These two photos show Merimbula Bay. The one on the left is looking northward over the STP, and the one on the right is looking southward. So Merimbula is a town on the southern coast of New South Wales, Australia, about 350 kilometres south of Sydney. Its location is shown by the red marker, and also here with respect to Sydney. Merimbula Bay is approximately 7 kilometres long and is located between the regional coastal towns of Merimbula to the north and Pambilla to the south. This project required the development of a model for the investigation of hydrodynamic processes that occur within and surrounding Merimbula Bay, and for plume dispersion modelling to assess the fate of treated wastewater discharges. This figure illustrates the location of several important features and data sources for model inputs and for model calibration, including the existing beach face outfall here in blue and in orange, Green Cape Weather Station for wind data, Eden Tide Station for tidal water levels, Merimbula and Pambilla Lake water level stations, and the long-term oceanographic data mooring off Haycock Point, deployed by Manly Hydraulics Laboratory for a period of 19 months. The model was developed using the Delft 3D modelling suite, with the intention to start with a 2D model and extend it to 3D. This figure shows the model grid and the 3 open boundaries, extending about 16 kilometres offshore, and this figure shows the model bathymetry. 5 potential calibration events with different key drivers were identified from the long-term mooring data. Manly Hydraulics Laboratory also undertook 2 field data collection days to investigate the spatial distribution of local currents and water quality in Merimbula Bay and further south around Haycock Point. These events were considered for calibration to assess spatial performance of the model. These 2 figures are examples of the forcing tide and wind field used in the model. And these 2 figures at the bottom show the ADCP transects during the 2 field data collection exercises. Boundary conditions for the Merimbula model were complex, as they are not only tidally driven, but require the influence of the East Australian current. ROM's modelled currents were adopted for boundary conditions on the north and east boundary for specific calibration events. This figure on the left shows the model boundary segments used with the ROM's boundary conditions. Each of the 3 open boundaries was divided into 5 boundary segments. Excuse me. In these 2 figures, examples of the prescribed daily current boundary condition derived from the ROMs are shown by the thick coloured lines. Also shown are depth averaged Haycock Point ADCP data by the thinner light blue line. With the ROM's boundary conditions, it was found that adequate calibration could not be achieved. The 2 main shortcomings identified were First, the 2 course daily time step compared to the short-term dynamic conditions observed at the mooring, as illustrated by the peaks and variability seen on this slide. Second, the fact the simulation was free-running and unable to represent the location and timing of East Australian current eddies. This slide presents model results versus observations for the first calibration event. It can be seen from these 3 figures here that there is a reasonable agreement between modelled and observed water levels at Merimbula and Pambia Lake and Haycock Point. The biggest discrepancy in water level is observed at Merimbula Lake, where there is reasonable agreement in phase, but the model tends to overpredict the peaks. The Merimbula Lake water level station is located at the peripheral inland edge of the lake and hence will be sensitive to bathymetry changes within the lake. This figure shows model results versus Haycock Point observations for both current speed and current direction. Currents do not show good agreement, with the model, the black line, under-predicting current speed compared to ADCP average speed, the blue line, and no real correlation is observed between peaks. Current direction is also not in agreement. Comprehensive sensitivity testing, including increasing the wind drag coefficient depicted by the purple lines, did not consistently improve agreement either. This demonstrates that the daily averaged ROMS output does not have the required temporal resolution to capture the current variability observed, and that the local processes, including winds, have not managed to bridge the gap observed in the mooring data. This initial calibration effort emphasised the role of offshore currents in driving observed nearshore currents and the need to develop prescriptive two-dimensional design boundary conditions based on observational data. The design current boundary conditions were derived from the long-term Haycock Point data through the following process. First, the ADCP data was depth averaged and a 1-hour rolling average applied. The normal component of the current velocity to the boundary was calculated, and then the hourly time series was extracted and any gaps were linearly interpolated. It is worth noting that the Haycock Point mooring was fortunately located at a site characterised by near free stream currents, despite its near shore location. This slide presents model results versus observations for one of the field data collection exercises during which spatial ADCP data was gathered. This figure again shows model results versus Haycock Point observations for current speed and current direction. There is good agreement with modelled current speed, the black line, generally aligning with the depth average mooring speed, or lying between the depth average and minimum recorded value. In these spatial plots, the modelled vectors show a reasonable match to the measured surface currents during the ADCP transects. For this event, the model generated a clockwise eddy in Merimbula Bay, which is supported by the transects shown by the red vectors. There were some discrepancies in the precise location of flow separation offshore in the vicinity of Haycock Point and current magnitudes. However, the model demonstrated to a reasonable degree the overall spatial dynamics observed in the bay. Adopting design boundary conditions as we have in this study does introduce specific constraints or limitations to both the model and calibration. The main constraints are the following: that the model is prescriptive and not responsive, and largely restricted to simulating known observed behaviours. Design boundary conditions are not perfectly compatible and as such produce anomalies and instabilities, although these are restricted away from areas of interest. For two-dimensional model calibration, observational data is simply depth averaged for comparison to model results. And design boundary conditions and calibration will include any inherent limitations or errors with observational data, including human error, equipment calibration, loss of data requiring interpolation, and targeted calm condition field days. This study has demonstrated a complication in choosing a regional model product for boundary conditions for specific event calibration. It has also demonstrated the invaluable role observational data plays in projects. Because projects are subject to timeline and budget constraints, the following are suggested key considerations from the outset regarding model boundary conditions and development. If adopting boundary conditions from a regional ocean model, consider those models with higher grid resolution, higher temporal inputs and outputs, and those that incorporate data assimilation, not just hindcasting. Most importantly, if adopting regional ocean model boundary conditions, conduct preliminary simulations to test if the large-scale boundary effects, in conjunction with local processes within the coastal model, are able to reproduce observations. Obtain a deep ocean mooring dataset if there is the possibility of adopting a sloping water level algorithm or elevation gradient boundary condition. And obtain sufficient high-quality ocean current data, fixed and spatial, for event calibration. Numerical models are not an exact science, as they approximate very complex processes, and open ocean boundary conditions are known to be challenging. The key considerations outlined here will present a greater opportunity to develop representative boundary conditions for future projects. Well, that brings us to the end of the presentation. Thank you very much for listening, and I'd be happy to answer any questions. Thank you.